single parity, what happens in single parity is that one extra bit is added to a block of data bits. So one extra redundant bit or parity bit or whatever you call it. Yes, so one extra bit is added to a block of data bits. So it's a very simple technique. You just have to add one extra bit. It is simple, and the redundancy is also not that much. So only one extra bit is being added to a collection or a block of data bits. But obviously that's what it is. So it comes with disadvantages. That first of all, it can only detect an odd number of error bits in a block. So if you have an even number of error bits in one block, it will not be able to detect. And also it cannot tell you about the extent of errors, whether a block of data bits has 1 bit in error or 3 bits in error or 5 bits in error or 7 bits in error. It cannot tell you how worse is the damage. It can just tell you there is an error. So let us consider an example. Let us look at this. So these are data bits. That's a block of data bits. How many bits do we have? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Okay, so we have 7 data bits, and we are discussing single parity error detection technique. So we have to use even parity. So the extra 1 parity bit has to be added based on even parity. So what will be the resulting sequence? So if you've forgotten about even and odd parity, so basically when we add an extra bit, we have to decide which parity technique to use, and either we use odd parity or even parity. And very simply what it means is that when we are using even parity, the total number of ones in the sequence including the extra bit, that should be even. And when we are using odd parity, so the total number of ones including the extra bit that we will add, that should be odd. So in case of even parity, we have to add an extra bit here. So that should be, what do you think that should be? Yeah, what should be the resulting sequence? So the resulting sequence, it should be 0, 1, 1, 0, 1, 0, 0. So that's our data bits. And then the extra bit that we add, because it is even parity, the value of the last bit should be 1. Because the last bit, when it is 1, that will make this, if you count the number of ones now, that becomes even. So the even parity condition is satisfied. So now when you add an extra bit, and based on even parity you will assign it a value of 1, and now when you check, the number of ones is even. The number of ones is even. So this is your code word. Now from here to here, that was your data word. These were all data bits. But now with the addition of this extra bit, this whole is now called a code word. So a code word has some data bits and a parity bit. So here is your parity bit, and all of these are your data bits. Okay, so this will be your resulting sequence if even parity is used. So now coming over to the next technique within block coding schemes, which is called BCC, or block check character or block check code. There are a few names for this technique. It is also called frame check sequence, and the idea is to apply the concept of parity now onto the blocks of bits, multiple blocks of bits. Okay, so it extends the error detection capability of a single parity bit, that is being extended. And obviously because of that, it overcomes some of the limitations of single bit parity system. So basically the idea is that you place check or parity bits on rows, you place check or parity bits on columns, and once you are done with this technique, you basically have one row which entirely consists of the check bits or the parity bits, and that extra row is basically called BCC. That's where the name comes. Obviously it has its limitations as well, as we will discuss with an illustrative example on the next slide. Okay, so let's discuss this example. Here I have given you a few words. So we take a few data words. Here we have taken 5 data words. 1 2 3 4 5 data words. So these are all the data bits, 7 bits, 0 1 2 3 4 5 6 7. Yes, 1 2 3 4 5 6 7. So every data word consists of 7 data bits, and we are placing one extra parity bit indicated by P here. So different books, they say that this side is the first bit. Some books they say that this side is the first bit. So in some texts you will see an extra parity bit added on this side. In some texts you will see an extra parity bit added on this side. So I'm basically discussing both examples. In the previous slide I discussed the other example where I added a parity bit on this side. So right now I'm using a different example where I'm adding a parity bit here on this side. Anyways, so these are your 5 data words, and you have to add a parity bit to every word, single parity bit, based on even parity. So based on even parity, you have to guess what should be the value of the parity bit. Should it be 0 or should it be 1 for every word? So as we have done on the previous slide, if you follow that example, you can see that the values of parity bits will be such that from these data words you come up with the code words which look like this. So this column here, now that column, which is basically this column, that column is, these are all parity bits. Okay, so we have our code words, the 5 code words here, and once we have the check bits for every row, now we need to add the check bits for every column. So we will continue to use the same parity, even parity, and now I need the value for, if I add an extra parity bit here at the end of this column, what will be the value? Similarly, for every column here I will need to add the value of parity bits. So based on even parity, when we do that, this is what we get. This is what I get. And as I mentioned in the previous slide about the discussion on block parity check scheme, that this extra whole row of parity bits is added, and that is what is called BCC. This row is called BCC. Okay, so that basically completes our encoding process. This completes our encoding process within the BCC scheme. So very quickly repeating, one parity bit in every row. Once that is done, then one parity bit in every column. Once that is done, then we have this BCC, and now we will send the code words in the same sequence as originally received. So word 1 will be sent first, then word 2, then word 3, then word 4, then 5, and then finally we will send BCC. So that is the sequence in which they will be received at the receiver. So the receiver will receive them in the same sequence, and the receiver will basically try to arrange them in the same order. That is what the receiver will try to do. Okay, so now let's consider another example for the receiver and see what happens at the receiver. So let's say this is what the receiver has received. So basically, as this figure shows, these are the data bits up until here, and these are the extra parity bits that we added for every word. So this was the data word, we added this parity bit, so this became our first code word, that is our second code word, with this being the value of the parity bit, the third, the fourth. Okay, so and then these are the parity bits for every column, and once all the columns, the parity bits for all the columns are complete, then that becomes our BCC. So this is so these were generated at the transmitter. This is showing you the receiver side. So let's say this is what receiver received. Yes, so this is an example where the receiver received this. So the receiver arranges them in the same sequence and now checks them. So starting from row by row, assuming even parity, it checks whether the value of parity bit satisfies the condition of even parity in that row or not. So even parity, this row should have even number of ones. There are even number of ones, so that's right. no error in this row. Now coming over to this row, the total number of ones in this row should be even, but it is odd. Yes, it doesn't know anything, it just counts the number of ones, and it sees that the number of ones in this row are not even. It's odd and they should have been even. So it detects that there is an error in this row. Okay, now it comes to the third row and checks the number of ones. It's even, so no error. Now comes to the fourth row, checks this row, the number of ones are even, so no error. Now comes to the last BCC, checks the number of ones here, number of ones are even, so no error. Okay, so that's where the process of error detection is completed, you can say. So now it detected error in the second row, so it can request the transmitter to retransmit the second row. It can request the transmitter to retransmit the second row. So that's what will happen. Now let's say we want to go into a bit of more detail. Let's say that once it is done with the row checking, it also wants to check the columns. Okay, if it is capable, if it has time, let's say it also wants to check the columns. So let's start by looking at the columns. So we'll start with this one. The number of ones in this column should be even, they are even, so no error. Coming over to this column, the number of ones here, the number of ones are odd, there is an error. Okay, so it marks that okay, this column has a problem. And now third column, number of ones should be even, that's fine, no error. Number of ones even, no problem. Number of ones even, no problem. Number of ones even, no problem. So it has detected an error here in this column. So it detected an error in the second row, it detected an error in the second column. So their common junction, okay, so the bit common between them is this bit here. So that means that this bit is in error. So if you want to extend the error detection capability to error correction, for correction it needs to identify the location of the error. So if it is able to identify the location of the error, then it can correct it also. So if this bit is an error, what will it do? It will replace it by 1. So if this bit gets replaced by 1, this row will not give any error, this column will not give any error, so the problem is solved according to the receiver. So in this case, the error in one bit has been detected, and if we apply the row checks and the column checks, then we are able to detect the location as well. Or if we just do the row check or just do the column check, we will just detect the error, we will not be able to identify its location, but here the location has been identified. So that is how the receiver tackles this problem. Now let's look at another example. Let's look at this example. Okay, so once again same procedure. Row number 1, number of ones even, no problem. Number of ones odd, okay, so this row has an error. Number of ones even, no error. Number of ones odd, there is an error. Number of ones even, there is no error. Okay, now let's continue this error checking column wise. Number of ones even, no error. 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 So column wise it doesn't detect any error. Row wise it detected errors in 2 rows. So now it is not able to tell you which bits are in error. It is not able to pinpoint. Okay, so only errors were detected without location, because it couldn't find which column had an error. It only knew 2 rows had an error. Now I have highlighted them, so I've told you which bits are in error, but actually this one it doesn't know. So in that case, obviously it has to just tell the transmitter to retransmit row number 2 and row number 4, because there were errors in those rows. It doesn't know which column is there. There is another example here which has three errors. So this row no error, this row has got no error as per the error checking mechanism, no error, yes error. Yes, so up until now row wise checking has revealed that this row has an error, this row even has got no error. Okay, let's do column wise. No error, no error, no error, error, no error, and no error. So based on its error correction, what will it say? That this row and this column had an error. So the common bit between them is this one, whereas actually these bits were in errors, but it was unable to detect that. In fact, it concluded that this bit is in error. So what will happen? It detected wrongly that in row 4 column 4 intersection there is an error. So once it made a wrong decision, it will say, okay, this bit is an error, let me go and change it. So it will change the value of this bit, and now instead of 3 errors we end up with a sequence having 4 errors. So it thinks one bit is in error, so it corrects it, making 4 bits in error. So depending on the scenario, there are limitations in this technique as well. It can only detect, or it can detect with location, or it can wrongly detect, or it can detect without location. So all sorts of possibilities are there. Okay, so now we start looking at another technique for error control, that is called CRC, or cyclic redundancy checksum. So in this CRC technique, basically there is involved division of two binary sequences. So one binary sequence is obviously your message sequence or data word, you can say. So these are all data bits, and the other is called the CRC generator polynomial, which is usually fixed and pre-decided between transmitter and receiver. So whatever polynomial the transmitter uses for coding, the same polynomial will be used by the receiver for decoding. Excuse me. So the way it works is that you have to divide the message by the polynomial, but this is binary division. It's a little bit different from our ordinary division. So you have this message and you have to divide it by a polynomial, but before division you have to add some extra zeros here at the end of the message. You have to add some extra zeros, and the number of extra zeros that you will add, that depends on the highest power of this polynomial. So in this case here, when you want to express these polynomials or this polynomial as an equation, this is basically, this represents x power 0, this represents x power 1, and this represents x power 2. So you know the significance of the bit positions. This is the x power 0, 1 is the least significant, this is the least significant, this is the most significant, and these bits basically they represent these powers. It is called a polynomial because it can be expressed as an equation. So basically this can be represented as an equation. So this can be represented as x square plus 1, because the coefficient of the middle term x power 1 is 0. So it's basically 1 multiplied by x square plus 0 multiplied by x raised to power 1 plus 1 multiplied by x raised to power 0. So that's what we get. So this polynomial, as a polynomial, that is the equation. So from the equation you can guess the polynomial, from the binary combination you can guess the expression. Anyways, so I was telling you that before you start the division you have to add some extra zeros here, and the number of extra zeros here, that depend on the highest power of this polynomial. So in this polynomial the highest power is 2. So whatever is the highest power, you add that number of zeros here. So in this case we will add 2 zeros here. As you can see, these 2 zeros are added. That's before the start of the division. Okay, now we start the division. So when we do the division, it's better if you look at this division in the traditional way, just like we do. So normally we put the number here, we put the other number here, so that it's easier for you to see. And now we start the division. So 101 times 1 is 101, and here now we do modulo 2 arithmetic or XOR operation. So we do the XOR. So these, when XORed, it becomes 1, these XORed, it becomes 1, and these two, their XOR result is 0. But we discard that 0 because that appears here, it has got no significance. So if during this division process, if there is a 0 on this side, we just keep ignoring it. You can put a cross in its place. Because that is not significant. A 0 in the center is significant, a 0 on this side is not significant for further steps. Anyways, to get a 101 here, we bring this 1 down here, and then we again multiply 101 by 1. We get this, we again do XOR. So that's a 1, that's a 0, so we cannot cancel this 0 now, so we will retain this one. We can put a cross here, and then we bring this 0 down. Once again continue the division, we get 101, and now as you can see, you get this 1 here, and now these two are cancelled. So we can put 2 crosses here. These are 2 crosses. I'll put this cross here as well. Anyways, so we have this one, and then we bring this one down. Still the number is smaller than that, we put a 0 here, and then we bring this 0 down, and then we do it, multiply by 1 is 101. We again do the XOR, a cross will come here, and now we have the final 0 here. We do again multiply by 1, and ultimately that's what we get. So that's where we stop. So this is the remainder. This remainder is called the CRC checksum. This remainder is called the CRC checksum. This remainder is appended to the message. So the extra zeros we added, in the place of those extra zeros, we add the value of the remainder, whatever that value is. So we replace those zeros by the remainder. So instead of these 2 zeros, we have the remainder, and that is what we get. So this is now the message with the CRC checksum. That's the new generated message with the extra parity bits added. So that is your code word now. Now this code word is transmitted. So as part of encoding process, first we find the checksum, we append the checksum to the message, and then we transmit that code word, which is a combination of data bits and parity bits. So we've added 2 parity bits here. So that is how the encoding is done. Okay, so now we come to discuss the receiver. Okay, and with the receiver, you have to remember that the receiver needs to know the polynomial that was used by the transmitter. So the polynomial is known to both the transmitter and the receiver. And what you have to remember is that CRC is particularly suitable for such scenarios where there are burst errors. So that is an error control technique very much suited for burst errors. Anyway, so coming over to how the receiver does it. So basically the receiver receives this sequence, as you can see on the screen. So this is what the receiver has received with CRC. So it divides it by the polynomial which is known to the receiver. So once again we do the division just like we did at the transmitter, similar procedure. And once the receiver is finished with the division, if the checksum is or the remainder is 0, then it means there is no transmission error. But if the remainder is non-zero, then it means there is a transmission error, and then it can request the transmitter for a retransmission. So basically receiver, that's one way how the receiver checks it. The other way the receiver can do it, basically remove the extra bits. So remove these 2 bits here and then do the division, just like what was done at the transmitter. So when you don't consider those extra bits and do the division, you get the remainder, which is actually the checksum. So if the receiver does that method, removing these 2 bits and then doing the division, it should get the value of checksum, which should be the same as what is receiving here. So if that is If they both are the same, then once again that means that there is no error. So that is how the receiver can do it. So just a quick recap of CRC I will do in the next slide. So these are some of the applications of this technique. It is very much common. The CRC is used in many different applications, and basically, as you can see in this table, some of the practical applications I have mentioned here. So CRC 16, for example, means that is a 16-degree polynomial. CRC 32 means that is a 32 term or a 32-degree polynomial. Similarly, 40 means that is a 40-degree polynomial. So different CRCs patented are used by different companies and their applications. Now in CRC, as you might have realized by now, that the data is treated as a binary number, and that binary number is divided by another binary number, which is called a polynomial or a generator polynomial, and that division is done using modulo 2 arithmetic, that is binary arithmetic with no carries. And as a result of this division, we get a remainder which is called the checksum, and that is appended to the data, and then it is transmitted. So that is the basic procedure of how the CRC technique works. So CRC is basically a technique for error detection, but it can be used for correction. So it is mainly designed and used for detection. However, with some advancement and with some careful planning, it can also correct a single bit error in a block, but some conditions need to be satisfied. First of all, the length of the message has to be determined in advance and has to be agreed by both the sender and the receiver. So fixed message length will be used. That's the first thing. And then secondly, a generator is carefully selected, a generator polynomial value selected so that it can be used to determine the position of position of errors anywhere in the message uniquely. So not every polynomial will do that, because we need a reference table so that we are able to pinpoint the error to its location. So now coming over to the example of how we can use a CRC for error correction. Let us say we have this 4-bit generator polynomial 1011, and we generate an error correction table with the bit positions. So the table has got some numbers from 0 to 7, and they are basically the background working is not shown, but they are in the order of position 0, 1, 2. So 0, 1, 2, 3, 4, 5, 6, 7. That is how it will work. And this is our message polynomial. Okay, so with this message polynomial, we will append our CRC. Okay, so these 3 bits here, the extra 3 bits, they are our checksum 0, 1, 0. That is our checksum appended to our message. Okay, so we added extra 3 bits. Why? Because our generator polynomial, this term is x raised to power 0, x raised to power 1, x raised to power 2, x raised to power 3. So we added 3 extra bits here. Okay, so this is our message with the CRC, and let's say that is what was generated at the transmitter, that is what was transmitted. And for example, let's say this is what was received. The receiver obviously does not know what was transmitted, it just knows what was received. So let's concentrate on this. I just let you know for comparison. So when the receiver performed its division at its end, it got a remainder. It should have got a 0, but it got this. Now this remainder now can be used to detect the position of error, because this, it corresponds to the decimal number 3. And as I said, in this error correction reference table, these values are arranged in the order of positions 0, 1, 0, 1, 2, 3, 4, 5, 6, 7. So right now we've got this remainder here. This converted to decimal represents this. So we are talking about the position 3. So when we look at the position 3 in the error correction table, 0, 1, 2, 3, that's 4. So that is the value of 4. That means bit number 4 is in error. So in our received sequence, bit number 4 is in error, this bit here. So it identifies the error location, and then obviously once you know which bit is in error, the correction is very simple. You simply change the value of the bit. So if it is a 0, it becomes a 1. If it is a 1, it becomes a 0. So that is how the error correction takes place. Okay, so that's the end of this lecture. Thank you.